Alright, let's try this again. I actually made this video and then the computer crashed and I'm remaking it. So, let's talk about chapters 8 and 9. Okay, the basics of chemical bonding and some theories of bonding and structure. So this is a chapter where we talk about Lewis dot structures, we talk about molecular shape and geometries, polarity, something called hybridization, as well as electronegativity review and things of that sort. Okay. So we're going to start by talking about the different types of bonds. Okay, a bond in general is an attraction between atoms within a molecule. Okay, there are three types of bonds that exist. We have ionic bonds, okay, which are electrostatic attractions between ions of opposite charge. They transfer electrons. We have covalent bonds that exist and share electrons between the atoms. And we have metallic bonds, which are attractions between atoms within a metal. Okay. The major focus of this chapter is covalent and the occasional ionic. Okay. We're going to start by doing a little bit more on ionic, and then the rest of the chapter is covalent based. Alrighty, so let's kind of run through and talk about some basic properties of ionic compounds. Okay, there's always a metal with a nonmetal, positive with a negative. These are highly exothermic when they form. They release a lot of heat, so they have a negative delta H value. They are crystalline, which basically means that they exist in a repeating pattern. So it would be like NaCl, NaCl. They are very ordered and organized. They have a high melting point because of their strong electrostatic attraction, and they tend to be soluble in things that are polar. Like dissolves like, polar with polar, nonpolar with nonpolar. Ionic is the most extreme polar you could possibly be, so that's why ionic compounds dissolve in things like water. Okay. And you can see here for the formation that it's an electron transfer from a metal to a nonmetal. Okay. As a review from last chapter, metals that give up their electrons usually have low ionization energies, okay, because they want to be able to easily remove an electron. Okay, less energy makes it easier. And they often transfer to a nonmetal that has a high electronegativity or electron affinity, which should make sense because those mean want electrons. That's why nonmetals are negative usually and metals are positive. Alright, so let's talk about ionic compounds and their energy. Okay, ionic compounds are very stable. Okay, they're very stable because the attraction between their ions of opposite charge makes them this way. Opposites attract. Negatives want to be near positives because in the end, most things want to be neutral. They form a solid lattice, which is based on something called lattice energy. And this lattice energy is officially defined as the energy required to separate 1 mole of an ionic compound into its components. It is determined using Coulomb's law, which is a physics law that I have written there in black for you. It is energy equals K, a constant, times Q, the charge of your ions, divided by the distance between the atoms. Okay, so charge is whatever the ion's charge is, and the distance between the atoms is basically the atomic radius. We're not actually going to calculate lattice energy. We're just going to kind of talk about how to determine when something has a greater or lower lattice energy. Okay, so lattice energy in general is going to increase as Q increases, so as charge increases, because that's the numerator, or as distance or size decreases, right? A small denominator leads to a larger value. Okay, so if the numerator increases, obviously E goes up, and if the denominator decreases, E also goes up. right? If I take 4 divided by 4, I get 1, but 4 divided by 2 is 2. So the types of questions you'll see is something like this. It may ask you to identify which of the following has the greatest lattice energy. The first thing you want to do with a problem like this is identify the charges of the ions. So Mg is plus 2, F is minus 1. Okay, calcium is plus 2, F again is minus 1. We know that oxygen is negative 2. I have 2 of them, so therefore their zirconium must be positive 4. The larger the charges, the greater the lattice energy. So automatically from that, you should be able to tell me that the zirconium is the largest of the 3, because 4 times 2 is 8, compared to 2 times 1, which is 2. Okay. If you were instead asked to put them in order, from greatest to least, okay, of the 3, zirconium would still be first, right? It's the greatest, it's got the greatest charge. The other 2 have the same charge overall. So what you would need to do is look at the size of the atoms. Well, they both have F, so that's the same. So you would compare Mg and Ca. We know from periodic trends that Mg is smaller than Ca in size. What that means is that Mg has the larger lattice energy. Okay, smaller means larger lattice. So MgF2 would be second, and then calcium would be the smallest. Okay, so always first identify charge, and if use the charges, and then if you have to, use size. All right, moving on. Let's talk about covalent bonds. Okay, all of this should be review. Covalents are nonmetals only. The electrons are shared. They have lower melting points compared to ionics. They're usually gases, not always, but they usually are. They're often soluble in things that are nonpolar, and they can form double, triple, or single bonds. Okay, ionics do not do this. They only form single. So single bonds are going to be longer than double bonds, and double bonds are going to be longer than triple bonds. That should make sense because there's less electrons in a single bond pulling the atoms together. Okay. Now for strength, it's the other way around. Single bonds are the weakest, then double bonds, and then triple. This is because a triple bond has 6 electrons, and a single bond only has 2. The book goes into a lot of detail on the formation of these. What I need you to know is that shared pairs of electrons act like glue in a covalent bond to bind the atoms together. Alrighty. Let's review Lewis dot structures. Lewis dot structures are based on the outer electrons, the valence electrons, and they are based 100% on the group number of the periodic table as long as they're from group 1A through 8A. Okay. The one exception is helium. Helium is in group 8A, but it only has 2 valence electrons. So it's the one that violates the rule. Couple of quick examples. Nitrogen is in group 5A, so it gets 5 valence electrons. And if you were drawing it, you would do this. Okay, they're all single before they get paired. Instead, if I had something like magnesium, 2A, 2 valence electrons, it would look like this. Okay, that should be reviewed from 110 and also most likely reviewed from some type of science class that you've previously taken. We're going to talk about the octet rule because the next slide we're going to draw structures for molecules. The octet rule states that atoms tend to gain, lose, or share electrons to achieve 8 outer shell electrons. There are quite a few exceptions to this. Okay. One that's really important is hydrogen. Even when it bonds, it only wants a total of 2 valence electrons. Okay, so it can only form 1 bond, and it's never the central atom. Boron is another exception. Okay. It only wants, even after it bonds, 6 total valence electrons. Okay. Metals also are an exception to this in general, but we won't really be working with metals too much. Finally, you can also expand your octet. So some elements, which we'll talk about later, can expand and instead have 10 or 12 valence electrons. That's covered in more detail later on. So we're going to talk about drawing structures for molecules. Back in 110, the molecule structures that you guys drew were fairly simple. Maybe something like CH4. Carbon has 4 valence electrons. I have 4 H's. Boom, structure is done. You were introduced briefly to double and triple bonds. So carbon dioxide, and things like that. Here, we are going to often violate the octet rule. Okay, so it's very important, because this violation happens a lot, is that you do this. Before you even draw the structure at all, I want you to figure out how many valence electrons are supposed to be in the structure. After you do that, you're going to write symbols for all atoms and connect them all with a single bond. Then you're going to complete the octets around all of the atoms. Okay. Then if there are leftover electrons, they get put on the central atom. And then something else that's important to note, if you have too many electrons in your structure, you have to change the bonds a little bit. So you'll be doing some double and triple bonds, okay, which we'll go over in some of our examples. Some additional hints. The least electronegative atom most likely goes in the center, okay. The number of single dots can tell you the number of bonds, but you'll see I put an X there. That's not always true in here because we violate the octet rule a lot. And then oxyanions don't tend to usually follow the normal rules, which we'll do a couple of examples of those. What that means is that something like BrO3 or even SO3, sulfur initially is supposed to have just 2 bonds, and Br really should only be allowed to make 1, but it can make more than that. Okay? So we're going to do some examples. I'm going to do a couple of them, and then I'm going to have you guys try a few. All right, I started off pretty simple here with NH3, and then they get harder. So nitrogen has 5 valence electrons. Each H has 1, but there are 3 of them for a total of 3. So overall, I want 8. Following the rules on the previous slide, I've summed up my valence electrons. I'm now going to write symbols for all the atoms and connect them with a single bond. Okay, so N goes in the middle. And then I fill the octet only on N. And then I count my dots. When you count, you should get a total of 8. 2, 4, 6, 8, because each line is 2 dots. Fairly simple example to start. Let's move on and make it a little harder. So for HCN, H has 1, carbon has 4, nitrogen has 5. So we need a total of 10 electrons. Okay, whenever you see a carbon, it always goes in the middle, no matter what. So carbon's in the middle. I'm going to connect the others with a single bond, and I'm going to fill all of my octets. I'm going to go through and count my dots. 2, 4, 6, 8, 10, 12, 14. I have too many. When I have too many, I have to add in double and triple bonds. I can't add any bonds with the H and the C because H only wants a total of 1 bond. So I'm going to add a double bond here. When I do that, I'm now sharing those electrons. That means carbon loses 2 and nitrogen loses 2 because they've been replaced by that bond in the middle. And I count again. 2, 4, 6, 8, 10, 12. I still have too many, so I'm going to share more electrons. So I put the double bond there, and then I'm going to remove 4 more. Okay, again, because they're sharing those dots now, or sharing those electrons now. And I count once more, and when I count again, 2, 4, 6, 8, 10, I'm good to go. So my structure should look like this. Okay. You'll notice that carbon is still in contact with a total of 8 valence electrons like it's supposed to be. So 2, 4, 6, 8. Nitrogen is as well. 2, 4, 6, 8. Okay. Whenever you have 2 extra electrons, that means you're going to end up with a double bond somewhere. When there are 4 extra electrons in your normal structure, you either have a triple bond or 2 double bonds forming. Let's do one more. SF4. Okay, I count my valence electrons for this one. 6, 7 times 4 for a total of 34. I draw my structure. Okay. All the F's go around the S's. Add my dots. When I count my valence electrons, I get a total of 32, right? Each F has 8. 2, 4, 6, 8. 8 times 4 is 32. But I need more than 32. So this is that additional rule where we're violating the octet rule. Extra electrons always go on the center. So I just add them there on the S, and it violates the octet rule. Okay. At this time, oh, hang on, we got to talk about ions real quick, and then you will have a chance to try a few. So if you have an ion, here's what you do. If I was counting my valence electrons for this one, Br is 7, O is 3 times 6, and this -1 counts as an electron. Okay, so when it's negative, you add 1, and if it's positive, you subtract 1. So when you add these together, you should get a total of 26. When you're drawing the dot structure for an ion, you draw it the same way you normally would, but you put it in brackets, and you put its charge on the outside. Okay. Now that being said, I would like it if you tried the remaining 4. Please pause the video and attempt these now. I would like you to please check your answers. You'll notice for the first one that I drew 2 examples. Honestly, either of those would be fine. We're going to learn about something called formal charge and how to determine which structure is more plausible coming up on the next couple of slides. Hopefully everything else looks good. It does not matter in this example here if you put like the CLs both here and the H's here, as long as the structure is drawn like this with the right substances around it, you are good to go. Okay. So hopefully you did okay with that. I do have some extra practice posted on dot structures as well as molecular shape and polarity and things along those lines. Alrighty, so let's move on. we're going to talk about formal charge, okay? Something you should not have covered in 110. And the formal charge is the charge an atom has if each bonding pair was shared equally. Basically, it's a way to kind of figure out, hey, did I put these atoms in the right place? Okay, did I put the bonds the way they're supposed to be? The sum of all the formal charges for something is always equal to either the charge of the ion or an atom. Okay, and if it's an atom, it would be completely neutral. You want them to be fairly close to 0, so you want to have a small range between your numbers. Okay, and then if needed, the more electronegative atom is more likely to have the negative formal charge. So just for review, electronegativity increases across and decreases down. Okay. The equation for formal charge is this, and we're going to do an example. Do not worry. It's the number of valence electrons for that particular atom minus half the bonding electrons, which is basically just how many bonds, the number of bonds attached to it, minus all of the non-bonding electrons. Okay, and it's of each atom. So you do this for each atom. Okay, we're going to do an example, and then I'm going to have you guys try some stuff for me. So the example I have here is Cn -1. To determine the formal charge, I have to do the dot structure first. So carbon is 4, nitrogen is 5, this is 1, a total of 10. Okay, I go through my whole process. In the end, you should get this structure. Okay. I'm going to find the formal charge of carbon and the formal charge of nitrogen. So for carbon, we know it has 4 valence electrons. There are 3 bonds here. Okay. So it should be 4 minus 3, the number of bonds. And then it has 2 non-bonding electrons for a total of -1. Nitrogen has 5 valence electrons. It also has 3 bonds. And it also has 2 valence electrons. So the formal charge of carbon is -1, and the formal charge of nitrogen is 0. Okay. Not terrible, hopefully. This equation is not obviously provided, so you will need that. Now, the type of question you're more likely to see is something like this one below. Okay, it says draw the 3 possible structures of SCN and determine which is correct. Okay, so what I would like you to do is try to draw the 3 structures. You don't move the atoms, you're just going to move bonds. So carbon's going to stay in the middle for all 3, and then you're just going to move the bonds around. So you should end up with some multiple bonds, and you're going to kind of arrange them differently. Okay, you really should end up with like a structure with 2 double bonds, and then 2 various structures with a triple and a single. So I would like you to pause the video and try to draw the 3 structures for the SCN ion. These are the structures you should have been able to come up with. Okay, valence electron-wise, S is 6, carbon is 4, nitrogen is 5, and then the -1. Okay, so you have a total of 16. You connect them all initially. You fill all the octets. When you count those, you get 20. Okay, that indicates that you need some double bonds. And so you should have ended up with something like that. And then I said to just move the bonds around. So you have 2 double bonds. In the next structure, you have a triple and a single. And in the final structure, you have a single and a triple. So you don't want to move the atoms, you just want to move the bonds. Okay. So now what we're going to do is we're going to find the formal charge of each element in each structure. And then we're going to determine which one is most likely correct. We want a small range of numbers. And if we have to, we also look at electronegativity values. And the more electronegative element is the one that will get the negative charge. What I would like you to do is pause the video and find the formal charges for all 3 structures and try to figure out which one is correct. So hopefully this is what you came up with for your numbers. Right away, right off the bat, okay, you should have been able to cross this guy in the middle off because of the range. So this is a huge range, right? 1 to -2, very big range of numbers. So automatically that guy's gone. Definitely not the right structure. For the other 2, in one of them n is -1, and in the other one s is -1. Okay. In the rules, the more electronegative element is going to get the negative charge. So you look at your periodic table. Okay. Let's transition to that real quick. Here's N, here's S. Electronegativity increases across and decreases down. N is going to be more electronegative. So because N has a greater electronegativity than S, N is more likely to be negatively charged. Therefore, this structure would be more plausible and more correct. Let's continue. We're going to real quickly kind of run through resonance structures. Resonance structures are really similar to what we just did. It's when there's one of 2 or more Lewis structures for a single molecule. The actual molecule is a blend or an average of all structures. And we're going to use a double-headed arrow to show resonance. The only difference between the structures here always is the placement of electrons and bonds. Okay? We never move the atoms around, just the bonds and the electrons. So for ozone, which is O3, we can have this. Or we could have this. Notice they're the same, but the bond has moved. And you would put a double-headed arrow like that to indicate that they are resonant structures of one another. Okay. What I would like you to try to do is this practice problem. You should get 2 possible structures. Please pause the video and try this now. Please check your answers. What I would like you to notice is the only thing that changed was the location of the double bond. So it was here, and it moved here. All right, let's move on. One more slide before we'll take a break. Let's kind of talk about the exceptions to the octet rule. Sometimes you can have an odd number of electrons. This is extremely, extremely, extremely rare. Okay, the one example that I was able to come up with was this one. N has 5 valence, O has 6, so there's a total of 11. When you draw its dot structure, it ends up looking like this, which is weird and strange and not normal. I don't test on dot structures with an odd number of electrons ever. You just need to know that it is a possibility. Okay. You also can have an incomplete octet where they want less than 8, which we've already talked a little bit about. We said earlier that boron only wants a total of 6 valence electrons instead of 8. So if I draw its dot structure here, boron has 3. F together is going to be 21, 7 times 3, for a total of 24. So I draw the structure here. And we get a total of 24. And boron is happy because it only wants 6 electrons. Finally, we have the expanded octet, which we also talked about already. Only certain elements can do this. They have to have a d sublevel and some d orbitals available, even if they don't use them. What that means is they have to be in the 3rd energy level or higher. So for us, it has to be the 3rd row or greater on the periodic table to be able to expand. And the reasoning is because they have a d orbital that they can expand into. So the first 2 rows of the periodic table cannot expand their octet. Okay. We already saw this example earlier. I drew it on a previous slide. We had to add the extra dots on S. And when you look at S, you get a total of 10 electrons around it. The other example here is PF5. P has 5. These would be a total of 35. P would go in the middle, and the 5 Fs would just kind of be around it. Again, it has 5 bonds, which means 10 valence electrons. Another good example would be something like SF6. That does exist, and that would be sulfur having 12 valence electrons around it. Okay, so you really should start practicing these dot structures and kind of getting used to all of the exceptions to the rule. As I said earlier, there is some practice that is available online on D2L. That's where we're going to stop, and we will pick up here another time.